So now this one's asking, is HCH3CO2 a strong or weak acid or base? That's actually a great question. So we have CH3COOH. I prefer to write it like that because it actually helps me see it a lot better. And now that I know it's that, this is actually just acetic acid. So with that being said, though, let's actually focus on the question at hand here and make sure we actually have the right molecule. So 2 C's, H3 here, and H at the end, and 2 O's. Okay, so we do have the right one here. And is it a strong or weak acid or base? So with this, we first need to write out our dissociation formula. CH3COOH. Okay, and we actually only know that because we have to actually draw it out. I would actually start with that first. Sorry about that. So CH3COOH, for example, right, would actually be like this right here is acetic acid. Now the reason why I actually drew it is because you notice that how it's positioned, right? These carbons with the hydrogens, okay, they don't interact with the as in these are not the hydrogens that are given away. It's actually here with this resonance structure, or soon to be resonance structure, is where the hydrogens leave. So this hydrogen here, okay, I'm gonna circle it a lot, is the one that gets out. Okay, that's the, in a sense, the acid complex of CH3COOH, allowing this to form a resonance structure as I mentioned earlier. Point being, though, okay, is that so if we were to write this formula in terms of the dissociation formula, right, it'd be this, okay, double arrow, okay, CH3COO minus plus H plus, okay. So with that being said, okay, based on that, we can say, because it's actually given a hydrogen, this is now defined as an acid, okay, making this its conjugate base. When the hydrogen is in the product side, that typically means that it's being given away, okay, making, at least in your half reaction, okay, making that molecule an acid, okay. So that's an acid with its conjugate base. So at least now we can say that it's an acid. Let's just write it down here, okay. And now we need to know whether it's a strong or weak acid. So face value, I'm going to tell you honestly, you cannot determine whether it's a strong or weak acid unless you've just memorized a list of strong acids. The good news is that there aren't many, but that's just the unfortunate trick to it. The other way to know whether it's a strong or weak acid is that if you haven't memorized a list of strong and weak acids in your head, hopefully you've been given a Ka table, which is a dissociation table. Well, actually it's just going to be K, but Ka is for acids, so dissociation for acids. Okay, now for Ka, the greater the Ka, okay, the stronger it is at dissociating, as in like separating, making it a stronger acid because it's able to, in a sense, form more of, I guess in this case, the hydronium, okay. The greater the Ka, the greater this thing splits apart, okay, and because it's splitting apart, there's more protons floating in the solution, okay. And we actually have barriers of how we figure that out. For Kas that are between 0 and 1, okay, these are what you consider weak, okay, relatively weak acids. And then for any Ka greater than 1, this is what you define as a strong acid. So we have now 2 barriers for what we are looking for in terms of the Ka. And hopefully you were given an actual sheet, okay, and we go over to our acid sheet here. We're looking for acetic acid, okay. So CH3COOH, there we go, acetic acid. What is this Ka? it's at 1.76 times 10 to negative 5. Okay, and you can already kind of see the answer here. Anything greater than 1 right now just says strong acids. That's all you need to know. Okay, so with that being said though, this number, is this greater than 1 or between 0 and 1? Making sure you pay attention to that exponential factor, 10 to the 10 to negative 5, you will know that this is between 0 and 1. So with that being said, because this is the Ka of acetic acid, this is a weak acid, okay? So that is your answer there, okay? And just as a disclaimer, you will never or should never get a Ka that's less than 0 into the negatives, because it doesn't make sense for I guess molecule to become even less dissolved. That makes sense. If you start out with a solid, you don't get more solid by putting it in a solution that has nothing but water. It needs actual constituents to be able to form itself back. But point being is that exactly, you won't get a Ka less than 0, and you need that to find out if it's a strong or weak acid. You can use a formula to find whether or not it's an acid or base, but you need your K values to actually know if it's strong or weak. Okay? Yeah. So yeah, this is correct. Actually, there is something. Let me see. The smaller the value, the stronger the acid or base is. Yes, exactly. So they're talking about pKa and pKb. So that's just it's almost like Ka, but it's negative log Ka is equal to pKa, and pK is kind of like the pH. The lower it is, the closer you get to 0, the stronger the acid. But yeah, so this is correct. Now let's move on to question number 7.